to start the class this afternoon. My name is Yinan Huang. Now I'm an associate professor in the Department of Civil Engineering, NTU. And I'm also part-time here in Ankara, so very nice to see all of you. It's my pleasure to open today's lecture. So for those of you who are not here yesterday, the speaker today is Professor Santiago Pujol, who is now the director of Quake Center in New Zealand, also a professor in University of Canterbury. So, and who is also ACI fellow and participate in many ACI committee. Sorry, and I believe you are here for the post-earthquake reconnaissance survey for the 2016 Tainan earthquake, right? Yeah. So Professor Pujol is a big promoter for drift-driven design of buildings, who is the topic of this short course. So without further delay, let's put our hands together. Welcome, Professor Pujol.
Thank you very much, Dr. I'm relieved that you came back. Let's see if this works. No, something's not working. I prepared a little summary for what I tried to say yesterday. That's the right input over there, maybe? Remote for the projector. Yeah. All right, sorry about that. So, I thought I should start trying to summarize what we said yesterday. I talked about the Japanese experience. I mentioned the work of Narito and Shiga and how they've been building very stiff and also strong buildings for quite a while. We also looked at buildings that they built in Chile, and we also noticed that those buildings tend to be quite stiff and they use a lot of wall. I mentioned the Kazan index that quantifies both amount of column and amount of wall, and I tried to make the case also that the evidence suggests that buildings with a lot of wall do well. And in general, I tried to make I tried to make the case that stiff buildings with short periods tend to have less drift and therefore less damage. In that sense, The idea is that we've been paying too much attention to the acceleration spectrum that speaks of inertial forces and too little attention to the displacement spectrum. And that except for short and weak systems, the linear spectrum is very powerful because nonlinear systems and linear systems are quite similar, at least in terms of displacement. Once again, except for short periods, and especially so for weak systems. So in that sense, a linear spectrum, again, can help us a lot, and it's best and easier, frankly, to talk about a spectrum where the spectral displacement is directly proportional to period. That helps us deal with these nonlinear structures with short periods. That's the summary of what I tried to say yesterday. Yes, we also said, by looking at actual data, that of course the period elongates as the structure cracks, and more so when it yields. But the effect of that longer period seems to be counteracted by increased hysteretic damping. When we were looking at actual measurements from displacements in buildings, we noticed that the first mode tends to dominate the response, and that the mode shape that we get from linear analysis is actually not far from the shape that the structure, nonlinear structure, takes. And that's all very convenient. So all of that forces us to make sure we know how to estimate both period and mode shape. So again, that's a summary of what I tried to say yesterday. And then I thought I should address some questions about these points. I didn't get too many questions. When I got back to my room, I thought my inbox was going to be full of questions sent by email, but I didn't. So I imagined some questions that I would ask myself if I was sitting there. So I'm going to address those. To help with the questions today, I have a surprise. I have an incentive to force mostly the students to ask questions, or not force, but encourage the students to ask more questions. So the first question I would ask myself is, well, you're saying you want stiffer buildings, but in stiffer buildings, usually you also end up with more strength, because if you put more wall or bigger walls and bigger columns, even if you just have minimum reinforcement, you end up with bigger strength or larger strength. If the building has more strength, the accelerations are going to be larger, and I've read many times that sprinklers and ceilings and other equipment are sensitive to acceleration. So what about that? You're going to end up with more damage than those. The other question I would ask myself is, well, you're saying you just need a certain minimum strength, a minimum, but other than that, it doesn't matter. I don't believe you. You're saying that if I take a building and I put more reinforcement, the building doesn't get any better? I don't believe you. Next question that I sort of made up is, well, we're estimating everything, or setting everything up rather, to use linear response to estimate nonlinear response. That doesn't sound right. I know there's such a thing as nonlinear dynamic analysis. It sounds very fancy, it sounds very rigorous. It must be better than linear analysis. Okay. The next question I sort of dreamt up myself is, what about cost? You're saying, you know, make everything bigger, put more walls. That's going to cost money. What about that? All right. So let's just start from the top. Another way to ask the question on the top is to say, well, we want flexible buildings that drift more because we want to save the ceilings and the sprinklers. Well, this is what happens when you have buildings that are very flexible, meaning not stiff. This is what happens when you have buildings that drift too much. This is a photograph from Christchurch, New Zealand, where I live now. A photograph taken after the 2011 earthquake. All these are places where they used to have buildings, and the buildings now have been demolished. Those buildings had to be demolished because it was too expensive to fix them. And in many cases, the fixing referred to partitions and ceilings and so on. Not so much to the structure. The damage in the structures, in most structures, was fairly limited. But even then, they had to demolish many of these buildings. In many cases, again, mostly because of damage to partitions. Also because of uncertainty. There was so much cracking, and clearly there had been a lot of yielding, and therefore some of the cracks were quite wide. There was so much of that that engineers felt uneasy, and the public felt even worse. There was fear, and there was also insurance, generous insurance, so people would rather get their money and go somewhere else than fix a building and then hope for the best. You know, so the combination of generous insurance policies and fear and lack of confidence from the engineers essentially meant that 2 out of every 3 buildings, 67% or so of the buildings in the downtown area were demolished. A tragedy in many ways, certainly a tragedy for the reinforced concrete industry. Just imagine if you had to demolish 2 out of every 3 buildings in Taipei. Imagine the mess. Imagine the emissions, the carbon emissions associated with that. Now, 70% of the built area in downtown Christchurch is made out of steel, structural steel. Yeah, is that sustainable? Is that the best way to engineer buildings? You see, ductility saves lives, but it doesn't save the investment. Controlling drift, stiffness, saves the investment. In my mind, that's the main lesson from Christchurch. On the other side of the spectrum, I wanted to point out Sendai in Japan, the north of Japan. The day after the earthquake, Sendai was functioning. Sendai was in operation. The areas affected by the tsunami, this is in 2010, of course were devastated, but the city of Sendai, for the most part, was running. And I have this figure here that compares the shaking that happened in Sendai, or near Sendai, versus the shaking that we recorded in other earthquakes that became famous worldwide, like El Centro here, Northridge, Mexico City. They look like jokes next to Sendai. And even then, that city was up and running. Why? Because they had buildings like the buildings that Naito started designing 100 years ago. And therefore, you know, they controlled the drift and so on. But again, the question is always, oh yeah, that's a building on the outside, maybe the walls were okay, the structural elements were okay, but what about the ceilings and the sprinklers? We don't believe you that they don't get damaged so much in these buildings. The buildings must have been looking horribly inside. Well, this picture is not from Japan, this picture is from New Zealand. And this is what my colleagues in New Zealand fear a lot when I suggest to them that we should make stiffer buildings. Many of them say, no, we can't do that because we're going to have a lot of this. That's bad. My answer is usually, well, if you're worried about the ceiling, fix the ceiling. But don't mess with my structure. Those are 2 very different things. If you're worried that the ceiling is going to collapse, make a better ceiling. Make a better attachment between the ceiling and the structure. But don't handicap the structure to favor the ceiling. the structure is more important. And then recently we came across some very interesting data from Chile again. And this is fascinating, but it turns out that at some point in time, Chileans built outside their tradition. Instead of building wall buildings, like the ones I showed you yesterday, they built some frames for hospitals. I was told that this happened because the World Bank gave them some loans, and the World Bank told Chileans, we don't understand why you make these strange shear wall buildings. We want frame buildings, American style buildings. And so the Chileans said, oh sure, give us the money. We want the money to make more hospitals. And then they took the money and they, met the condition, which was build some frames. So these are all frames from Chile. No, sorry, these are data from frames and walls, or wall buildings from Chile. They all refer to hospitals. And what we've done in collaboration with this person belongs to the Chilean Ministry of Health. They have a very good inventory of damage that has occurred during several earthquakes. What we've done is we've classified the damage from severe to none. All of this damage refers to damage to, again, ceilings and sprinklers and so on. And what I think you must have seen by now is that the frames, which are the darker bars here, tend to have much more damage in, again, acceleration-sensitive components, well, so-called acceleration-sensitive components, than the wall buildings. Unexpected. I didn't expect this. No one expected this. I heard this in a presentation that someone was giving out. Well, this person, Renato Calcaño, he was giving this presentation at my university in Spanish. And he said this, not with the data, but he said it in words. Someone was translating, and the translation wasn't quite as direct as this. But I thought I'd heard wrong. So I approached Mr. Calcaño and I said, did you say that you see more damage in ceilings and sprinklers in the frames than the walls? He said, yes. I said, how can that be? And he said, I don't know, but I can show you the data. So he's been sharing his data with us, which is very generous. And this is amazing. We started looking for evidence that acceleration-sensitive components get more damage in the stiffer buildings. We can't find the evidence. There are anecdotes, but not much evidence. So, but this is the best we've been able to find. If you have data, please let us know. Otherwise, what we're doing is we're trying to run more tests or corroborate this through tests. Oh, I see. I got to put this in here, otherwise it doesn't work. Yeah, so we're trying to run tests. So we made this facility where there's a slab here and there's another slab up above, and then we can hang from it different ceilings. And then we can shake them like that. In some configurations, we also have walls that interact with the slab below and the slab above, and also interact with the ceilings. And we can control the motions in these two slabs to try to replicate or mimic what would happen in a stiff building versus what would happen in a more flexible building. And then after we do the shaking, we go and count how many tiles have collapsed or are about to collapse, or how many of these aluminum angles get bent, and so on. So far, we can't tell a big difference between what happens when we move the slabs as if they were in a story up above in a stiff building versus as if they were somewhere in a flexible building. But yeah, you would say, of course, given the beautiful facilities that you have here for testing, you would say this is kind of a silly Mickey Mouse test. We're moving things only in one direction, and the actual earthquake, everything goes in both directions. Actually, many directions. Certainly we can do better, and hell yes, you can do much better. But that's why we're trying to collaborate with you, and thanks to Pu Wen and Chia Chen and Professor Wang and so many of you, we're running this large test down in Tainan to try to see what happens in a building when we have braces here that stiffen things up versus what happens in the same building when we remove braces and we get more drift and less acceleration. So we have a lot of non-structural elements going in there trying to address that question. Okay, so that was my long answer to my first question to myself. Questions about my own question? Okay, let's go to the next question then. I don't believe you that you say strength doesn't matter. So, okay, I don't blame you. It's hard to believe. It doesn't matter as long as you have some minimum strength. You have to have some minimum strength. And frankly, to stay out of trouble, the minimum should be whatever the code requires. Easy. It can be less, but you don't need to go that far. But here, to illustrate what I'm trying to say, I have a Mickey Mouse demonstration here. And yes, I understand it's all analysis, but I also showed you some sort of hard evidence from tests yesterday. So I mentioned this program yesterday. It's called Stera 3D. It's available to you on the Dropbox folder I gave you. I built a model in it. And building a model in this thing is very easy because you can go from floor to floor, up or down with these arrows. See, now I'm on the first floor there. You specify weight and height, you specify spans, and to add a column is as simple as clicking on one of these boxes. Of course, you can change the number of spans and so on by clicking somewhere here and specifying the type of structure you have, so you can change the number of spans. You can also add beams. So say I could add columns and beams. And then if I want to add a column, a wall, I just click there once more, and instead of a beam, I get a wall. So it's very easy. You just click, 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 and you build your structure very quickly. You can specify the properties of everything in a fairly simple manner, and that's what I want to do now. I want to play with the properties of the columns and beams that I have here. So you see the column, and I have the same column everywhere to make my life easy. The column looks like this. It's 600 by 600, and it has D22. 4 corner bars, plus 2 bars in what they call here X side, which is this area bound by this dotted box, and then in the other side I have 2 more bars. So I have a total of 8 bars. There are D22s at this moment. We can play with that. And then for the beam, which I specify here, I have also D22s, 2 at the top and 2 at the bottom. And what I've done here is I have run this earthquake, or this building through an earthquake. I think I used the Kobe 1995 north-south motion. For this amount of reinforcement that I just showed you, I got almost 40 centimeters of roof displacement, which is a healthy displacement. So what I want to do now is run this again in front of you here. You know, like the magicians do, nothing on this side, nothing on this side, and show you the magic of changing the reinforcement. What happens when I change the reinforcement? So remember that number, 40 centimeters we got in sort of the weak configuration. This file is on the folder I gave you, so you can do this on your own. You can try to replicate this if you want. To run this, it's not too hard. Oh, but before I run it, I need to change the properties. So again, I'm going to go to the column here, and I'm going to make the bars D32. That essentially doubles the reinforcement, more or less. So D32s, and D32s everywhere. I changed all the reinforcement in all the columns. And then let's do the same for the beams. We're gonna make them D32s. D32s. Done. Let's double check. Columns, D32s. Yes. Beams, D32s. Done. This is not a very good building, as you can tell, because it doesn't have shear wall. It's an okay building, but not great. To make sure we sort of read the new properties that were changed here, you click on these boxes. This is sort of an isometric view. This is a perspective view, and then this allows you to do at least an initial analysis, meaning you can do a model analysis and you can get the period. You can do what all of you love, which is you can make the building dance, right? And you can see the different modes. It's all free. Even better, you can run static and dynamic nonlinear analysis. And it's fairly easy. So for the dynamic analysis, of course, you have to specify an earthquake. So I'm going to specify here, Kobe, north-south. In fact, go here. This is your folder. Yeah, this is the right. Kobe, north-south. Or if you go to this folder that I created for you called Effects of Strength, Try It Yourself, you can go to this folder called Stera 3D where you can download the executable, and then under there's an example there, and this is sort of the example that comes with the software, but also there you have some other earthquakes if you want to try some other earthquakes. So let's load Kobe north-south, 1995. Pretty strong earthquake, 0.8 G, peak ground velocity almost 90 centimeters per second. Yeah. Pretty strong, pretty demanding motion. There are two ways to execute this now to run the dynamic analysis. One way is you click on this red arrow there, and that runs sort of a full-blown analysis and with all the output files, element, moments, forces, rotation, the work. Or you can do sort of a cheap preliminary run where you look at one thing at a time just by pressing the play button there. If I press the play button there right now, all that we're going to see is sort of the color of this line changing. It will become red just to tell us how the base is moving. Who cares how the base is moving? We already see it there. What we want to see is how the top of the building and this displacement. So I'm going to press play now, and then the building is going to start moving, and we're going to see top displacement versus time. And I hope I don't get egg on my face, but I did try this, of course. But what we're going to see is that the displacement doesn't get much bigger. Remember what we saw was 40 centimeters per second, right? Ready? Or should we take our break now? See? Didn't displace half as much. We made the structure twice as strong, right? We doubled the reinforcement. The displacement is about the same. Again, everything has a limit. Everything has a limit. We're not talking about making the reinforcement ratio 10 times bigger. You cannot even do that, right? I mean, reinforcement ratio for the most part just ranges from 1% to 2%, right? So right there, just for constructability issues or because of the minimum we use, we're sort of constraining the problem a lot, number one. Number two, I built a 10-story building or so here. 1, 2, 3, 4, 5, 6, 7, 8-story building on purpose. If you try something very short and very stiff, that probably won't work. Again, for short period buildings, stiffness seems to make a difference, right? Not stiffness, strength. So everything has limits, but within fairly reasonable limits and within a fairly wide domain, the strength doesn't seem to be that critical. Play with it, and see what you get. Questions about that? Okay. Yeah, the next question is, in essence, you told us that you're going to use essentially linear analysis to estimate drift. We know better. We know there is a much better option, nonlinear dynamic analysis. You just run it there. You know, why don't I use that instead? Nothing wrong with using that. But remember, you always should have a way to check, right? It's not easy to push all the right buttons in a piece of software like that. For instance, in Stera, if I go back to Stera, you know, if you look under the hood, so to speak, you know, like in a car, there's all sorts of mysterious things going on in there. What damping should I use? And when you look at the options, they give you 3 options that don't seem very easy to understand just by looking at that, right? Options A, B, and C. That looks very cryptic, very difficult to interpret. You have to go to the manual and try to figure out what's what. And what's the right option anyways? Who knows? I mean, damping is such a made-up thing. You know, the structure really doesn't have any dampers in it, right? The structure just leaks energy for whatever reason. We don't even understand what I don't understand what the reason. Where does the energy go? Is it heat? Is it noise? Is it... Anyway, I do recommend, however, while I'm here, that you use this second option in the Stera. Because that second option refers to damping that is proportional to the updated stiffness matrix, as opposed to the first option, which refers to the original stiffness matrix. The updated stiffness matrix will give you a better answer. Will give you essentially less damping. And the other thing that I suggest strongly is that you try not to be too optimistic about the amount of damping you assume. Try to be pessimistic, meaning use a small damping, 1 or 2%. And yeah, everyone uses more, or very often people use 5%. But how do you know? Try to use small damping. That actually correlates better with measurements, small damping than bigger damping. So the point I'm trying to make is that nonlinear structural analysis is not necessarily super transparent either. You still make a lot of assumptions. But that's not the question I want to address. The question I want to address is whether it's any better than linear analysis, which is what I'm trying to sell you here, because if nothing else, it's easier. So let's entertain that through this slide. Maybe. There we go. The slide speaks for itself, I think. It says calculated drift versus measured drift. That is measured story drift ratio. I measure maximum story drift ratio. So we've looked at actual models, physical models that have been tested in the lab on shape tables, eDefense, University of Illinois, back at Purdue, in many places. I don't think we have data from Taiwan here yet. We should have the data. So that's the y-axis. In each of these models, we go and look at the story drift ratio in each story, and then we pick the maximum from all the stories. That's why we have the M there. So measure maximum story drift ratio. And then the x-axis is what we calculate. On this side, I have what I would calculate from a single degree of freedom system by projecting the response of the single degree of freedom system to the structure using the mode shape. And I'll show you how we do that in a second, just in case you don't remember. So that's this plot here. And this plot has what we get from nonlinear dynamic analysis from programs like Stera or OpenSeas. I think this actually was done with OpenSeas. But you can, pick the program of your preference and see if you can do better. But I would argue that the plot on the right is not much better than the plot on the left. Again, detailed nonlinear dynamic analysis, or as they call it, time history, right? What a silly name, time history. Isn't history always about time, right? When do you talk about history without referring to time? Why do they make up these terms? I mean, it was always dynamic analysis, and then someone decided time history, and then everyone said, oh yeah, time history. What a silly name. But anyways, I don't think it's any better. At least when we've tried, it doesn't work any better for us. All right, so that's that. Questions about that? So no questions from the students. But again, I have a surprise for you. I know you're going to be asking questions here in a second. Okay, so next question is, what about cost? All this stuff you're talking about, adding concrete left and right, that's going to cost an arm and a leg. You know that expression? An arm and a leg? Cost an arm and a leg? It's going to cost a lot. I guess the expression comes from going to war. You come back and you have one fewer leg and one fewer arm. You lose an arm and a leg. That's very expensive. Yeah. So first, I'm going to quote Naito, the same guy who've been quoting, who started thinking about this 100 years ago. He looked at numbers and he said, you pay 5% extra for all the wall I'm asking you to add to the building, but that's 5% of the cost of the structure. And the structure, I don't know what it is like here in Taiwan, but in most other places, in New Zealand and Colombia and the US, the structure roughly costs 20% of the total cost. So that's 5% of 20%, which 1% of the total cost, total, including the land and the finishes, equipment, the realtor fees. Do you have realtors here too? People come to the house, with fancy attires and expensive cars, and then they tell other people, yeah, buy this house, because it's very nice to look. You have that here, I imagine, no? Yeah. How much do you pay them? In New Zealand, we pay them 5% of the sale price. 5%. In the US, we used to pay them 6% of the sale price. And then a couple of years ago, someone asked the question, why are you charging me 6%? And then the realtor said, well, that's what the association, the National Association decided. Well, that's price gouging, that's against free market. In the country of free market, well, not anymore. In the US, they were fixing the price. Companies cannot agree to fix a price in a free market economy. That's illegal, right? So there was a huge lawsuit, and they're supposed to give me money back because I paid 6% to the realtor. And then I filed all my paperwork. They haven't given me a dime back yet. But anyways, the point is, we pay a lot of money to bankers and realtor agents, and we pay a lot of money for finishes. This is not as much. It's only 1% of the total. Of course, that's Naito many years ago. We've done our own numbers for New Zealand, trying to convince our ministry to reduce the drift limit. So I have this plot here that shows how much cost would change for different drift limits. In New Zealand, things got complicated because we also changed the seismic hazard. We realized we were designing for the wrong earthquake. We were designing for earthquakes that were too weak, so we had to increase the hazard. So this slide is complicated by that. The reference will be this sort of bar here, that's essentially a zero, no change. That's relative to the old seismic hazard, and that's relative to a frame. So this is sort of the point of reference. A frame building designed for the old hazard. But I don't want you to get too distracted by that. I'm just going to point at a few, three specific bars here. This one. This is how much extra a frame costs today to the new hazard, a frame, relative to our point of reference, a frame a few years ago. This is how much a wall building will cost extra if we design, again, to the new hazard and to much less drift. It costs the same, or maybe less. The difference being frame versus wall. It's much cheaper to build wall buildings. It's very expensive to frame or to form, to create form or to build a frame. It's very expensive. And even if we design for 1%, the wall building is not much more expensive. So there is quite a bit of evidence, and there are other references that show this is affordable. The last thing I wanted to say here, before my surprise, is that there are a couple of typos in the book. And so I made this tiny URL that shows you our typos. You know, that's a list of our typos. So I apologize for that, but that's how it goes. Now, the surprise for the students. I have prizes for you. If you ask a question today, even if it's not a very good question, and I will never tell you so, I have these vouchers for, I think, coffee and some pastry at Starbucks. Yeah? But you have to ask a question. Okay. I'm done with my own questions. Do you have questions of your own? Hey!
I'm not a student. Yesterday you mentioned, I think you mentioned explicitly that yes, we should control drift, and does that mean, well, I guess in your, for what you're strongly arguing for, what would then be the role of things like plastic hinges, collapse mechanism, and even like pushover analysis?
A good role. We're going to look at mechanisms here pretty soon, because we do have to admit that, again, the building has to have a lateral strength, and the best way to estimate lateral strength is to do either what they call pushover analysis. That's another funny term, pushover. Pushover, if you look it up in the dictionary, it refers to someone you can manipulate. So yeah, if you call someone a pushover, it's because, you know, kind of insulting them. So I always thought it was such a silly thing. It's like to call the analysis silly analysis. Non-linear static analysis. Yeah, it's important because it tells us whether the structure does have minimum base shear strength or not. And I'll show you how I go about doing sort of very simple pushover. So it has a very good role in that sense. It tells us whether we have enough strength, more than a certain minimum. It's very easy to do when you do it right. And then it has a maybe even more powerful use. When we identify the mechanism, we can learn a lot about what could happen in the building. For instance, if you realize that the beams are going to hinge at each end, then from that we right away have a very good idea for what's the worst shear that could happen in the beam, right? That's the shear associated with hinging at each end, and we're going to cover that. So it tells us that, you know, let's call it plastic analysis or pushover analysis. It tells us what the worst scenarios are in terms of the internal forces that could occur in the building. Now you also mentioned hinging. So of course that's related to the idea of mechanism, right? But also it's important to realize what is going to yield and what is not going to yield, so you can detail it better. So in that sense, realizing sort of the plasticity in the system is very important too. And don't get me wrong, I do advocate for less drift, but that shouldn't come at the price of less detailing or worse detailing. I think you need to have both, belt and suspenders, right? I don't have suspenders right now, so that's I'm being very conservative, but the building should have both. You see, you control drift, so you can manage the damage. But we have to admit that there might be a scenario that goes beyond the drift we expect, and in that case we need the ductility. So we can accommodate larger drifts before things go bang. Yeah. In my mind, ductility, detailing, hinging, so on, that's a safety net in case things go wrong. Very good question. Do you want
That's okay. Leave it for the students here.
yeah, if they don't ask questions. Other questions? Yeah. Are you a student?
Yeah. Yeah.
Okay,
Yeah.
go ahead.
I'm very curious about the budget issue, and I'm happy to see you mentioned about the cost. And I have one question: is since the seismic resistance has been improved, will the expect service life still 50 years, or we can make the building have a more longer lifespan?
Excellent question. Yeah, 50 years is not enough in my mind. We should be looking at 100 years, I think. And that goes against in the same direction. Therefore, we need better buildings, right? Yeah. We can't recycle our cities every 50 years. Yeah. Okay, other questions? I have more prizes. For some reason, the university thought that I have breakfast twice a day. Can't have breakfast twice a day. So that's fine. All right, that's very good. Okay, let's switch to another question that I have, but this is more a question as to your background or about your background. I was told that all of you guys are very, very good with structural dynamics. So where's the mouse? Where's my mouse? There it is. So I wanted to ask you the following question, if I can't find the darn mouse. There we go. Sometimes it disappears. Come on. Oh yeah, there it is. So let's go here. There. Are you familiar with that idea? That you can superimpose modes to understand a multi-degree of freedom system. That if you have the response, whether it's response over time or peak response, as in, say, displacement spectrum or a spectral coordinate, so to speak, SD, you can multiply that times this factor, which is called what? Model participation factor, right? You're letting Professor Juan answer your question. The question is for you back there, not for Professor Juan. And then you multiply model participation factor times mode shape factor, right? The mode shape factor varies from floor to floor, right? From degree of freedom to degree of freedom, and this way you can project the response of the single degree of freedom system to whatever floor for whatever mode. And I've crossed out here modes 2 and 3 and beyond because the first mode usually dominates the response of a multi-degree of freedom system, at least for displacement. For forces and base shear, the story is different, a little tricky, but we can talk about it. And I have a video here that shows a structure with many degrees of freedom that we tested a couple of years ago. Yeah, you can see the second mode on it, but when you get it really moving, there's the first mode that controls the displacement. Okay, so I know that at least Professor Juan is familiar with this expression and how to project the SDUF to the MDUF, and I will assume the students are too. Yeah? Okay. So, with that in mind, I wanted to go back to where we were yesterday, which is here. Mouse, come back. Yeah, there we go. But I see it's time for our first break. We stopped here yesterday. We were looking at a multi-degree freedom system, a 7-story building. We're trying to find the period and the mode shape. And we're going to use those to calculate drift for a given earthquake, all by hand. Of course, you can always go and enter this into Stera 3D or whatever other program you like best and try to check my answers. But let's have our break. Let's have our break. So let's meet at the hour. That thing is fast. That's throwing me off. It's 5 minutes fast. Yeah. Oh, so that means I have 5 more minutes than I have. So bear with me. Let's get this to a more exciting point than I got it to yesterday, and then we'll have our break. So I stopped here yesterday. If you remember, I made some fake forces here, and from forces I obtained shear just by adding from the roof. And then shear divided by stiffness should give me the distortion of every story, right? I was able to boil everything in a story to one spring, which is a heck of a feat. But before I can do this, I need to express K as a vector, which I haven't done. So I'm going to do that here by just declaring a vector. And just to save space, I'm going to declare the vector horizontally like this and then transpose it, just to save some space like that. And then what I'm going to say is that all the stiffnesses were the same in all the stories except in the first story, which was, if you remember, 40% stiffer. And I called that ratio of the stiffness of the first story to the other stiffnesses alpha. So I can just do this. That's just a vector of stiffnesses like that. And the first story is stiffer than the other story. So that's all good. So why is this not happening? This array index. See, I have a mishtuko somewhere. Okay, so 1. Yeah. Oh, I think I know 1. Yeah. My problem is that mathematicians are funny. Mathematicians are special human beings. You and I, when we start counting things or people or so on, we start from 1. We say 1, 2, 3. Mathematicians don't do that. They start from 0. They start 0, 1, 2, 3. I don't know why they do that. Math that was clearly written by mathematicians. But you can change that. They realize that the rest of us think differently. You can change the place of the origin of the counting system to 1 if you want. Anyway, so that works. You see, this thing was unhappy because I was referring to an 8th entry in a vector that only had 7 entries, and that's why it didn't work. Okay, so now I have distortions in every story. From the distortions in every story, if I add them up, I should get the deflection, right? And so if I want to look at floor number I, and if I'm wondering how much floor number I is moving sideways, then all I need to do is add the distortions of the stories below. So the stories below look like that, and I'm going to add their distortions from the bottom towards the level that I'm looking at, which I'm calling level I. Like that. And now I have the deflected shape of the building. The best way to look at deflected shape is by normalizing it, and I'm going to normalize it with respect to the displacement at the roof. That is, I'm going to divide every entry in my vector here by the displacement of the roof. I need the left bracket. and the left bracket to indicate this is a sub-index, not a subscript, but a sub-index. So I'm going to divide by delta sub 7, and that now gives me a shape like this. Yeah, I've got to do this one thing at a time. I could also do this actually, now that I think about it. I can now just get rid of the I and just divide the entire vector by delta sub 7. Same difference. But now I have the deformed shape, just like that. And I'll show you in a second here, that's quite similar to, that's too many significant figures which bothers me. So yeah, that looks better. That's quite similar to the shape of a sinusoid. And I'll show you that in a second. But more interesting, I now have a shape and therefore can think of, again, the maximum potential energy of this thing while it's linear. And I can think of the maximum kinetic energy, equate both, and obtain the period of this thing, or at least the circular frequency, without having to run ETABS. After you do this, you can go and run ETABS all you want. And then the idea is that the answers should match. If not, I'm guessing you enter something wrong in the ETABS. Right? Okay, so that brings us to a break. So let's meet at the top of the hour again and we'll find the period of this thing. Okay? Thank you. Oh, the prizes are given only for public questions. So if you ask me a question here in private, then no prize tonight. Plotting in MathCAD is fairly easy. You just go up here to the plots menu and you insert an XY plot. Not hard. You have this sort of placeholders here where you can enter the variables or functions that you want to plot. So in this case, this refers to the y-axis. I'm just going to plot the floor number on the y-axis. Floor 0 refers to the ground, and floor 7 refers to the roof. The plot in blue here, the line in blue refers to the shape factor that I just calculated. And that's the blue line. Again, it kind of looks like a sinusoid, like a quarter of a sinusoid, and that's why I plotted a quarter of a sinusoid there in gray. And you can add more functions that you want to plot if you want to plot them by simply adding traces, or you can remove some of these traces. There's a lot you can do with this. Just for your information, you can change the limits of your plot by playing with these numbers here, like that. This is very flexible, very powerful, and I prefer MathCAD versus the other options I mentioned yesterday, BlockPath and SMath, because the plotting is much, much better in MathCAD than in those other options. You notice here, there should be a line from here to 0 to the base, but anyways, let me just use my hand to replace that. You notice the first story deflects less. Well, that's because we assumed the first story was stiffer. If you remember, we assigned a much bigger stiffness to the first story. Is this thing working okay? It kind of goes on and off. Okay. The other thing I should say here is that this is the typical deformed shape of a frame. We'll see in a second that a wall has a very different mode shape. Okay, so now that we have that shape, we can go on and say, well, yeah, that looks like a reasonable shape. Let's calculate potential and kinetic energy. Let's start with the potential energy. So what I'm going to do is I'm going to sum the products of stiffness and the square of the distortion. This is not the displacement of each floor, but it's the distortion of each story, delta, right? Stiffness times the distortion of each spring squared divided by 2 is the potential energy in each of the springs when the system is displaced the most. That's the potential energy. But interestingly, you can also obtain the potential energy this way, as the product of forces times floor displacements. These are floor displacements, not story distortions. Now, this force times displacement is work, and the 1/2 is there because you start from 0 force and you ramp up, right? So you can calculate potential energy either way. This is interesting, by the way. What I'm doing there is I'm just asking the system to calculate that summation. If I just press equal, I get something in joules. I'm talking about energy. But I can also ask for something in terms of, or as a multiple of PE, or as a fraction of PE, PE being this quantity that I just defined here. You notice that if I just type PE there, MathCAD shows PE in blue. Blue in MathCAD refers to units. PE is not a unit, PE is just a quantity. So you just press Control U, U is in unit, and then you can switch that back to just a quantity, PE, and then I obtain sort of a multiple of PE. Just a convenient way to compare two quantities. So that's potential energy. Is that cool? It's kind of high school physics, right? So far. Kinetic energy is not much harder, just like we did with the single degree of freedom system yesterday. We just multiplied mass times velocity squared. Times 1/2. But this time we have several masses, not just one mass. We have one mass per floor. And we gotta be careful with the velocity. We need to think of the velocity as omega times displacement. Circular frequency times displacement. Of course, what you should say right here, right now, if you wanted a prize, you should raise your hand right now and say, that looks funky because I don't know omega, right? I don't know the frequency, that's what we're after. So how's this gonna work? Well, we're going to equate this quantity and that quantity and solve for omega, right? That's what we're going to do. So one way to look at it is to take the omega out of that expression, like that. Just took the omega out of there, and then I'm going to call this quantity not kinetic energy, but relative kinetic energy, so to speak. And that allows me then to assign a number to a variable. You see here, I wasn't assigning a number to anything. This is, again, just for decoration, so to speak. This is just a symbol, it doesn't do anything. Here I'm actually calculating a number which would have some units, that doesn't have units of energy, right? I'll show you, right? If I try to display the result, it's something. It's not joules, it's something, because it's missing the omega, right? The omega square, actually. So that doesn't mean anything to me, so I don't even display it. But what that allows me to do is take the ratio of those two things, take the square root of that, and that should be omega, circular frequency. Does that make sense? All right. Then, of course, that's the period associated with that circular frequency. Pretty cool. You could argue, you obtained that estimate of period with a deflected shape that was arbitrary, right? This deflected shape was arbitrary because these forces up here were arbitrary. Yes, they are. But I invite you to revise the forces. You could argue the forces should be proportional to accelerations. And acceleration, you could argue, should be omega squared times displacement. So in that sense, you could argue that the distribution of forces should be similar to the distribution of displacements. You could argue, right? Go ahead, revise the distribution of forces to have the same shape as the structure. Doesn't make much of a difference. You still get 0.7. That only makes a difference if the distribution of mass is very ununiform or not uniform. So that's a very easy way to calculate period, or at least to check the output from a program. And we have now period and deformed shape. Okay, sorry, I don't know why I jumped back there. So if you have a different distribution of forces, the result seldom changes much. You don't have to worry about that too much. Questions about that procedure? Did you like it? Yeah, I like it a lot. Other people don't like it. Other people think, no, I can do better. I can do eigenvectors and eigenvalues. That's not too hard. Once you have the structure idealized this way, once I have a structure idealized this way, as a series of springs and masses, writing the stiffness of stiffness matrix. Writing the stiffness matrix for that is not hard. It's not hard at all. Because what we can do is we can move 1 degree of freedom at a time. Move 1 degree of freedom at a time. We move 1 degree of freedom 1 unit, say 1 millimeter or 1 micron, and see how much force occurs in these springs, and see how much force we need to apply to other degrees of freedom so that they don't move. That's the easiest way to write a stiffness matrix. So for instance, in the stiffness matrix I'm going to show you in a second, what I'm going to show you is the force that I need to apply to displace this 1 unit, and that would be, well, this is stiffness times 1, plus this is stiffness times 1. That would be the total force I need to apply here. You agree with that? If I want to prevent this degree of freedom from moving when I'm applying that force that I just mentioned here, I need to push back, right? With how much force? Well, with the force in this spring. So what that means is that the first entry in a stiffness matrix for this building will look like this. This is the stiffness of the typical story. If you remember, alpha times that is the stiffness of the first story. So what I have here is the stiffness of the typical story plus the stiffness of the first story. That's how much force I need to apply if I want to make the first degree of freedom move 1 unit. And then if I do that, I need to push back the next degree of freedom with a force opposite to that. Does that make sense, or should I make a little diagram? That's okay? Okay, well, if that makes sense, I want to ask the students if they could explain to me, well, let's say, why is this a 0? The idea would be, let's go to this. The idea there would be expand this very cryptic here. So again, we have springs and masses, like that. Now, it's impossible to draw with a mouse. I need to draw with the on the screen here. So I can do that. There we go. Alright, I want to do this. Duplicate. Alright. Sure. Keep that, and then, yeah, that's a little better. hide this, and then here I need. Where's the? I see. Okay, there we go. Missing my drawing tools. Where do they go? Here? No. Where are my drawing tools? Sorry, I'm used to be able to, sketch things by hand, and then we have a camera that projects. So I tried this morning. Should be able to do it. Why not? Oh, all right, that will do. So I have something like this. Right? And what I'm saying is I'm going to cause a unit displacement there like that. So this spring has to stretch, that spring has to stretch. Of course, that is the result of a force like that. The way we build a stiffness matrix is by doing that 1 degree of freedom at a time and keeping the other degrees of freedom for moving. So what I'm saying is that over here I have this much force. Times 1. Because I need to overcome 2 springs. This is spring and that spring. Over here, well, this spring is pulling this object sideways, so I need to push back with this much force. Remember, this is K typical and this is K for the ground. K typical, K typical, K typical, like that. How much force do I have to apply up here to prevent that degree of freedom from moving? You guys? 0, right? And that's why in the stiffness matrix, you will see, again, the summation of the 2 stiffnesses from the typical story and the bottom story. Then this is the force pushing that second degree of freedom back, and then we don't have to do anything to the degrees of freedom up above. That's how we built the first row here, rather column in this matrix, by just displacing the first degree of freedom sideways. Here we're going to displace the second degree of freedom sideways. So let's think about this one sort of one step at a time, because if we get this, you'll see that everything repeats from there on. So the idea there would be that now we're going to displace the second degree of freedom. So we're going to keep the first degree of freedom where it is. We're going to move this degree of freedom sideways like that. That's going to require us to stretch 2 springs, one right above and one right below. That's going to require us to push back like that and then push forward like that. So if this is stiffness is K typical and this stiffness is K typical, that means I need to apply a force of 2 times K typical that way, right? And then I need to push back with how much force? 1 times K typical here and the same here. And in the other degrees of freedom, I don't need to do anything, right? So that means, again, this is K typical times 2. And this is just K typical, negative, pushing back, and same here. Again, everything times 1 millimeter or anything. So that's why we have a 2, that's the 2 forces going one way, and the 2 other forces going the other way, and nothing else. And that exercise is repeated row after row. At the roof, things are different, because at the roof, there's only 1 spring below, and no spring above. And there you go. You have a stiffness matrix. Very easy. If you have a stiffness matrix, and you can write a mass matrix, which is even easier. I have one mass per degree of freedom, and they're all the same. And if I have something like MathCAD with me, I can do very cool stuff. I can invert matrices, like that. I can multiply matrices. And then I can solve this thing that the mathematicians call the eigenvector problem, which essentially gives us the mode shape for the first mode, which I already got, but also I get the mode shape for the second mode and the third mode and so on. Very easy. And I can also obtain the eigenvalues, which when you set things up like that, that means every entry here is 1 over a frequencies squared. Those are the frequencies for each mode. This building can vibrate into, up to 7 different ways. 7 modes. The first one, of course, all the masses are moving at the same time in the same direction. In the second mode, this kind of thing is going on. In the 7th mode, everything is moving each way. In the 7th mode, you will see a plus and a minus, a plus and a minus. And then these are the frequencies of vibration associated with each of those modes. And if we compare what we got before with our sort of high school method, with what we're getting here is the same. This is what I'm getting here. This is the eigenvalue here, which leads me to this frequency. This is what I'm getting from this mathematical solution, so to speak. This is what I got before. Same frequency. So you can solve the problem very many different ways. Choose whatever you like better. The real magic here, in my mind, happened when we boiled every story down to one spring. That's the crucial step here. That's what really simplifies the problem. In my mind, the real merit of all of this lies in this expression, which is not exact, but it's pretty good. And I invite you to enter this into Stera 3D and get the frequency, and you'll see you get about 0.775 seconds. It's pretty good. One trick, though, when you go to Stera, click on this, and you might want to change this value, because that value right there says the entire beam column joint is rigid. That's what that says. In our calculation, we assume the beam length goes from column center line to column center line. If you want to do that kind of thing, then you need to reduce this towards 0, but you cannot enter 0 there. You can enter something very small, though. You can enter something like that. If you enter 0, it doesn't work. Program crashes. But if you enter a 0 there, you should get, or something close to 0, you should get, again, a very good estimate of the frequency that would be very similar to that. And the mode shape is very similar too. Look, this is the mode shape that I obtained with sort of high school physics and mathematics, and this is the mode shape that I'm getting from the eigenvalue problem. Of course, my solution is approximate because I used an approximate deformed shape. If I go back and revise the forces that I apply, and apply forces that have a more reasonable distribution, so to speak, then I'll get pretty much the exact same value. Okay, so we got period, we know how to calculate period, we know how to calculate mode shape for a frame. Questions about that? Well, I think your question should be, I thought you were telling us that frames are not so good, that we should do walls. So how do I handle a wall, right? That should be the question. Well, let's do the wall. There are different ways to handle a wall. I'm going to assume that I have the same masses everywhere, the same masses, the same height, the same stiffness, and that I have for these tributary masses. Remember, I've assumed that I'm looking at one frame out of many, and the mass that I have signed at each level refers to sort of tributary mass. So I'm going to assume that in this tributary area, so to speak, of my building, I have only one wall that has this much moment of inertia. I did the math, and that translates into a rectangular wall with this thickness. A wall going from one column axis to the next. And that's a funny number just because I thought of, or the example was set up this way before I thought about sort of this equivalency. But I'm going to show you two different ways to go about estimating the period of a building with a big wall. This is the easiest way to think about it. This is a formula that comes from mechanics. That's the period of a cantilever with uniform mass. You can look that up. You can Google it. You can Google this. You cannot Google the other procedure I mentioned before. By the way, that other procedure of equating potential and kinetic energy, that's called the Rayleigh method. I don't think AI is very good with the Rayleigh method. AI would probably give you this okay. AI is, in terms of mechanics, AI is not so good yet. But this is easy to look up. Period of a cantilever. Pi is, of course, modulus of elasticity. This is the second moment of the area, the cross-sectional area. Mu is density. Mu is mass per unit of cantilever length. And the height is the height. That refers to the total height, 7 times the height of one story. That gives me an estimate of 0.38 seconds. That assumes, again, the mass is uniformly distributed along the wall. It isn't. It isn't. The mass is concentrated at floor level, right? That means the top of this cantilever is too light, right? Because the top of the real cantilever, the real wall, will have a full story up there. This will have maybe, in terms of, if I try to think of it sort of in equivalent terms, this assigns only half the weight of a story to the top of the cantilever. The top is too light in this model, so this is likely to be a little too short. So, there's an alternative, which is we can discretize the wall the same way we discretize the frame. What I'm trying to say is, instead of a bunch of translational springs and masses, what I want to do is, let me start with something clean. We can. Same trunk. Drawing tools go away. Let me try again. See. Okay. No. Whatever you tell me. No. Okay. Here we go. Great. So, yeah. Okay. So what I'm going to do is I'm going to take this cantilever. If this thing allows me. This cantilever. And I'm going to discretize it again into a series of masses, like that. But instead of translational springs, I'm going to put, that's a mass, that's a mass, that's a mass. I'm going to put in between, I'm going to put rotational springs. Rotational springs. So let me draw those in a different color maybe. And the rotational springs go where? Yeah, they go at the floor levels too. So I have a rotational spring like that there, and and then a rotational spring like that there, and so on. It's kind of an ugly picture, but I hope you get me. I'm gonna, instead of thinking of translational springs, I'm gonna think of rotational springs at each floor level. So instead of shear, I need to think of moments now. So I'm thinking of rotations at each floor level. Well, moment is the integral of shear, of course, so I can just multiply shear, again, from my force distribution that I assumed earlier. I was able to obtain this fake shear. These are all fake forces, they don't mean anything, but again, they're going to help me obtain a deformed shear. So I take each shear, multiply it by height, and that's an area. Under the shear diagram, if I add areas from the top of the building to whatever level I am to calculate moment, I get moment. Just integrating the area under the shear diagram. That gives me moment. And moment divided by flexural stiffness gives me curvature. M over EI is curvature. And if I have curvature, I should be able to obtain changes in slope, right? Curvature times length gives me change in slope, or rotation. This will be the rotation occurring at each rotation on the spring. The bottom of the wall is different though, because the bottom of the wall is stiffened by the foundation. At the bottom of the wall, I cannot have curvature distributed above and below the lowest rotation on the spring. At the bottom of the wall, right here, I can have bending or curvature, if you will, above the level of the spring, but not below, because this is the foundation. And I'm going to assume that's rigid. So I can have bending on half a story up here, but not half a story down here, as opposed to this rotational spring where I can have bending below and above. So this spring is a little stiffer in that sense. And that's why I'm going to say that the change in rotation that happens in the first story is half as much as the change in rotation that would happen elsewhere. So I have changes in the slope, or rotations, not changes in rotation. Changes in the slope or rotations at each level. If I add changes in the slope from the bottom up, I get slope. And once I have slope, I have it made. That this gives me the shape of the cantilever. Slope times height gives me translation. And when I add all the translations, I get the displacements, like before. If I add all the translations at each story, I add them all up from the bottom upwards, then I get displacements. And then I'm sorry, I used twice the same variable. I shouldn't do that. I should call this something different. This was curvature. And here I'm trying to think of mode shape. Let me call it like capital Phi. Or, not to break what comes below, I could call this just curvature, like that. Yeah. But what I'm doing here is I'm just normalizing the displacements, and I have obtained a new deflected shape. In this case, for my cantilever, it's my shape. And if I plot it, I obtain this, which is the shape of a cantilever, which is now close to the shape of a cosine as opposed to a sine. Let me sort of go through the motions again, just to make sure we're all on the same page. From my previous procedures, I had already defined forces and shear forces. The integral of shear gives me moment. Moment divided by EI gives me curvature at each floor level. I can multiply curvature times distances to obtain changes in slope. The first story is different because I cannot bend the foundation very much. But other than that, I should be able to add changes in the slope sequentially to obtain the slope of each story. And with the slope of each story, I can then obtain the distortion in each story, which added up produces deflection. And once I have that deflection, I can normalize it to obtain the shape of the wall. And I've done all this just to find this shape. Because once I have that shape, I can think the same way I did before. Using the Rayleigh principle, I can calculate potential energy. I can calculate it like before, force times displacement. That's easier to digest. Times 1/2 again. Or I can think of potential energy in these rotational springs as moments times rotations. And I have, of course, not one spring, but I have many springs, so I add them all up. That's a new way to, or a different way to think about potential energy. And kinetic energy takes the same shape as before, same thing. I take the ratio to obtain circular frequency, and from that I get period. We had a period of what? 3/4 of a second or so for the frame. The frame had 4 column lines, right? 3 beams, 1 per span. The columns were not trivial, 600 by 600. The beams were 900 by 450 plus slabs. Decent frame. Period, 3/4 of a second. Here, I replaced that entire frame with 1 wall. The wall occupies only 1 span, not the 3 spans, just 1. It's rectangular. It's not very thick. It's 200 mil plus thick. Look at that period. It's not quite half, but close to half the period of the frame. Roughly speaking, that means the drift in this building, even with just 1 wall per bay, if you will, or at least for this tributary area, the damage in this building is going to be much less. The drift is going to be much less. And then, before I go away from this, so I got 0.4 seconds or so, little more than that. When I applied the Googled formula for the cantilever, I had something slightly shorter. Again, that's because in this model here, I have all the masses concentrated at the floors, and the floor has, the roof has a full mass, right? The cantilever doesn't do that. The cantilever has sort of uniformly distributed mass. I can reconcile the 2 numbers. Remember, I got 0.38 before for the cantilever. I can reconcile the 2 numbers just to check my math by simply saying here something like the mass of the roof is equal to what? Come, 1 person at a time. Half the mass that I have assumed. If I just put half the mass there at the roof, this number becomes the same number I obtained for the cantilever. See that? Yeah. Because again, I'm lumping the masses at each floor here, full masses, and the cantilever that assumes the mass is uniformly distributed, the roof is lighter than it should be. But again, that's just to check the math. The mass of the roof is the mass of the roof. If I have a full slab there, I probably have the same mass as everywhere else. And that's why I have a note here that says the difference between this value and what we obtained before is simply that the cantilever assumes the top was a little lighter. Alright, so let's take a little pause there before I jump into how to combine a wall and a frame. Because that's usually what you have, right? At least in Japan. you always have wall and frame, and it's good practice, I think, to have a dual system. So before we tackle that, questions about my calculation of period for a frame by itself or for a wall by itself? Yeah.
Do we need to consider the shear rigidity?
It makes little difference in general. But if you have a squat building and a squat wall, it might make more of a difference. One of the chapters in the book, I forget the number, tells you how to consider the shear stiffness. Yeah. But for something like what I have here, a wall with an aspect ratio of more than 3, it shouldn't make too big of a difference.
Thank you.
You have a wall that has an aspect ratio of 1, maybe. It can make a difference. But again, there's a chapter there that addresses that. You student?
It's okay. It's okay.
No, it's not. No,
Student.
I need to get rid of it.
Right.
It's fine. It's fine. No.
You
You want
can
to
give it
point
to
out the
someone else.
next?
You can give it to someone else.
You can give it to a friend. You have friends?
So you need 2.
No, I need one for tomorrow.
Thank you so much.
Yeah, no, thank you. Okay. Other questions? Okay, let's talk about the wall and the frame together. And this is more difficult. But recently, a student in a class like this one had this idea, and we tried it, and it seems to work fairly well. His name is Leon Pledger, and he just wrote a paper about this. We'll see if it gets accepted, but it seems to work fairly well. He actually analyzed very rigorously hundreds of frame wall structures or dual structures, and the estimates of period he's getting with this approximation is fairly good. He says, look, to combine the frame, which is a system of translational springs and masses, with the wall, which is a system of rotational springs and masses, what I'm going to do is I'm going to think of the wall also as a bunch of translational springs. It's going to try to idealize the wall in terms of translational springs. How? Well, he says, easy. You already have shear and distortion for your wall at each floor. You could think of the ratio of shear to distortion as some sort of equivalent translational stiffness. Walls don't work that way. Walls, unless they're super short, they work as bending elements. But he says, as an approximation, I'm going to think of a wall as a bunch of translational springs. Yeah, so in a translational spring, stiffness is force divided by distortion. And I'm going to add, so I want to combine your wall and my frame, or the frame and the wall. I add the stiffness of the frame plus the stiffness of the wall. So we're saying now we have the frame connected to a wall and lined with each other, so to speak, or in parallel. So the total stiffness is the stiffness of the wall plus the stiffness of the frame. Okay, makes sense. I have an illustration of that here somewhere. Yeah, like that. So that's kind of the system I have in mind, something like this. Wall and frame are working together, if you will. It's not like we built the wall within the frame, they're just working in parallel. Okay? Once we do that, we repeat the same process we follow for frames. We find a new distortion for the increased stiffness by dividing shear by stiffness, and we add all the distortions to obtain displacement. These green boxes here simply mean you already defined that variable before, so that's okay. Again, we define then the shape and I wanted to show you how the shape changes. This was the shape of the frame by itself. Now in blue here, I'm showing you the shape of the system that has both wall and frame. The shape is very different. The shape is a lot more linear. Remember, the wall did this. The wall tends to drift a lot at the top. The frame does the opposite. The frame kind of comes back at the top. The drift is not so high at the top. When you combine the two, you get something fairly linear, which is nice. Or better distributed drift, which is good. You don't want drift concentration in your structure. And then we operate the same way. We find potential energy, kinetic energy, just like before. And from that we get frequency and period. And what I want you to notice here is that the period didn't change a whole lot, right? The wall really dominates the system when you combine it. Of course, there's always all sorts of possibilities. If you have sort of a flimsy wall and a robust frame, then the frame does make a big difference. But when you have a good wall, like the walls they use in Chile and some frames around it, the wall dominates the response. And that's what this shows. If you want to check things with Stera, I need to alert you if you go and read from Stera what modules of elasticity they specify. They have a long formula there. So beware of that. But yeah, I think that's what I got. No, we have something very important to talk about now. Modal participation factor. Once I have period and shape, the next thing I need to think about is how I'm going to project the response of a single degree of freedom to every story of the building. And the key to do that is the modal participation factor. This is how modal participation factor works. You have the summation of the masses of each floor times the shape factor for each floor. And in the denominator, you have the same except the shape factor is a square. And that's sort of a typical value for a wall building, something close to 1.4, 1.5. That is if the mode shape is normalized to a value of 1 at the top, which is what we've been doing, right? I take the displacements that I obtain and divide it by the top displacement, meaning the shape factor is always 1 at the top. So this is typical. For a wall building, you get something close to 1.5. That is, the roof is going to displace 50% more than a single degree of freedom with the same period would displace. Very easy then. If you have a spectrum, you can enter with the period, obtain a spectral displacement times 1.5. That tells you how much the roof moves. Very easy. And for a wall building. For a frame building, this factor tends to be close to 1.25 or so. So we have a way to project from the single degree of freedom to the multi-degree of freedom system. Easy. And then the next thing that you want to look at is where are you going to have more drift? So if we go back to our deformed shape, I think you would agree with me that the lower stories seem to have less drift and the upper stories seem to have less drift. In this dual system, the stories with more drift will be stories 3 and 4 up here, right? That's where you're going to find more drift. The question then becomes, how much more drift am I going to find in those stories? And the way I like to think about it is this way. You might remember that yesterday we discussed something we cannot find now. Here it is. Yesterday we discussed these plots. What we've done here today is essentially arrived at something like this for, again, a dual system. This is the deformed shape that I showed you yesterday. This was calculated 45 years ago. We can do the same today, of course. It took a lot of effort to calculate this 45 years ago. Now anyone can do it. by hand almost, thanks to MathCAD and similar software. So you can do this in your spare time. Something very cool they did here again is they can use this shape to produce this plot that shows you the drift occurring in each floor divided by the mean. If all the floors have the same height, the mean drift is just the roof drift or the roof displacement divided by the height. Right? And what this shows is that in the worst stories, the story drift may be 30%, 40% more. If you have a soft story, you could have 50, 100% more story drift than the mean. But if you have a uniform building without discontinuities, without soft stories and things like that, on average, the typical ratio of maximum story drift to mean drift is 1.3. If you want to be conservative, assume 1.5. Again, assuming you don't have a soft story. Let's see how much we got for our building. So what I'm going to do here next is I'm going to look at the differences between shape factors. And I see that between floors 4 and 3, this is the difference between shape factors. Then this is the difference a little bit higher up, and this is even higher up. So clearly the worst drift would occur here. And if I divide that essentially by the number of stories, that gives me more or less the ratio of peak story drift ratio to roof or mean drift ratio. You see, the idea would be that story drift ratio should be spectral displacement. Let me increase the size of this a little bit. If I take spectral displacement times gamma times, say, phi, the mode shape factor for floor, what did I say? 6, no, 5. Between 5 and 4, I'll obtain the worst. So if I take, I didn't bring this over here. If I do this, that should give me the maximum displacement of floor number 5 for this particular building. But we usually care more about the relative displacement between two floors. Well, I can do that by simply subtracting the same quantity, but for the floor below. That would be the distortion of the story between floors 5 and 4. Of course, I can factor things here and say that this is the distortion of the story between floors 5 and 4. And if I take that and divide it by, if I divide that by the height of one story, I would get story drift ratio. What I'm interested in is the ratio of that versus roof drift ratio. Well, I can do that by dividing all that by the roof drift, which would be SD times gamma times phi at the roof. And if I divide that by the total height, that gives me roof drift ratio. So this is the drift ratio for one particular story here. This is roof drift ratio or the mean drift ratio. Of course, a whole bunch of things cancel there, and you obtain that. And again, that tells you that in the worst story, the drift ratio will be 30% larger than the mean. Okay? All right. So keep those numbers in mind. Participation factor for this particular building is 1.4. The period we obtained among friends, 0.4 seconds or so. Right? There's no need to be very exact about period. The actual period of the structure is going to be very different. because there's flexibility in the foundation, right? The soil is going to mess things up. We'll never get the modulus of elasticity right. We don't exactly know what's going on in the beam column joint. Is a mess. So let's say that the period is 0.4. Model participation factor is 1.4. And let's say the worst story would see 30% more drift than the mean story, so to speak, or the roof drift. Okay? With those numbers and a simple spectrum, I'm going to calculate drifts for this building. Okay, but let's take a break. When are we supposed to stop? 5? Okay, yeah, so it's time for a break. I'm going to try to calculate drift for this one dual building that I made up. I'm going to try to calculate drift for this one building for the Kobe North-South 1995 earthquake record, I think from the JMA station. So I've imported the record into Mascot here. That's just as easy as saying read this text file. That is called Kobe 95. Someone was asking me how to import a record into Stera. So yes, you just go here and say File, and then you open your record, but the record has to be in a special format. It's not so important that the entries are organized in the form of a matrix that you read from left to right and top to bottom. But what is important for Stera is that you specify the number of entries and the time step. Okay? So that's all these files here under this directory called Wave. In the Stera folder, all those files have the same format. So all those files will work for you and Stera. However, for my purposes here, I converted one of those files into a single vector of entries. I just took the same file and reorganized it as a vector, and I eliminated the first entry that spoke of the length and the second entry that referred to the time step. So that's why you couldn't import this file into Stera. But that's what I wanted here. I just wanted a clean vector. I assign units to the vector, and the units in all those records, by the way, the default units in Stera are gals, centimeters per second square. Right, that's a gal. And then I can do things like this with my record. I can look at the maximum acceleration, or the minimum, or the absolute maximum, which is what I'm doing here. These are just, just getting the absolute value of the minimum, which of course would be a negative value. And that's again close to 0.8 G. Once more, you can display the units you want, like that. I'm going to go ahead and plot the record, just because I can. And for that purpose, this type of variable is very useful. You can try, sorry, it's rubbing a little bit against my clothes. Okay, maybe that's better. You can try, or you can define this variable, which is called again a range variable, by typing its name and starting with the first couple of numbers. When you type a comma, immediately you get this type of notation that allows you to define the variable. Alright, and that allows me to do things like this, where I'm plotting each acceleration entry in the record versus time, and time is simply time step times entry number. Time step was 0.02 seconds. So that's acceleration record from Kobe. To me, velocity is more meaningful than acceleration. And I'll try to explain why in a second, but for now, let me just say, I want to calculate the ground velocity. I should be able to do that, again, because I know some high school physics. I should be able to integrate the acceleration to obtain velocity. You know better than me, or maybe some of you know better than me, that's not always easy, right? In this case, the record has been corrected already, so that's not too hard. All I need to do is multiply each acceleration record times the time step. That's of course an area under the acceleration record, and if I add that change in velocity to the previous velocity, I can obtain a new velocity. Integrating in MATLAB is very easy, I think, very easy. You can do this in Excel too, but you need big columns of numbers and so on. I find this a little bit more transparent. So of course you can do this in MATLAB, you can do this in Python and so on. But again, I think this is more transparent. This is how we write math. In my mind, this is much easier to read than programming. And then once I integrate the velocity, or the acceleration record to obtain the velocity, I can look at the peak values. And again, you see the peak value is almost 1 meter per second. So I'm going to say the PGV is 90 centimeters per second, and this is the velocity history. Pretty demanding earthquake. I know in Taiwan you have had more demanding earthquakes, but let's say the rest of the world thinks this is very scary. Maybe not you. Okay. Before I go any further, I want to pause here for a second and talk about spectra. Again, all of you are probably very familiar with the acceleration spectrum, which looks like this. All right? All of you are very familiar with that. And if you were to plot the spectrum for an actual record, of course, you get some spaghetti. Oops, starts from down here. You get some spaghetti like that. Oh, that disappeared. Okay, Nathan Newmark, who in many ways was a genius, was able to look at things like that and say, oh, well, forget that. We can idealize that kind of shape into something much easier to work with that looks like that, right? That's what Newmark said. And again, all of you are familiar with that, and I presume the Taiwanese code has a spectrum that looks like that. What we seldom look at is the displacement spectrum. And the displacement spectrum can be obtained from the acceleration spectrum, remembering that more or less you can go from displacement to acceleration that way, or vice versa. And if you do that, what you obtain is a parabola here related to the straight line up there. And it gives you a parabola here, and then from here on you get a straight line like that. Didn't draw that very well, did I? Parabola like that. Yeah. That's the displacement spectrum. Yesterday I showed you some experimental data to make the case that because things are different for short period systems, we're better off assuming this is just a straight line all the way through. But safer, that's easier to just a straight line. Okay. When Newmark proposed these shapes, he said this value here, that value there, you can think of it as peak ground acceleration times some factor that he called amplification factor for acceleration. That's what he said, and you will find in most building codes that factor is anywhere between 2.5 or 4 or so, depending on what damping value you're using. Everyone seems to know that, everyone seems to remember that, every code, every book speaks of that. What most of the literature seems to have forgotten is that Newmark also spoke of this area here, past this period, which he called the region or the range of nearly constant spectral velocity. Of course, between acceleration and displacement, there is velocity. And if you were to look at the velocity spectrum, Newmark would say the velocity spectrum looks like that. And he called this range the range of nearly constant velocity. And again, what everyone seems to have forgotten is that Newmark also spoke of that as whatever the ground is doing times some sort of amplification factor, which he called the amplification factor for velocity. What that implies, to make my story short, is that the slope of the displacement spectrum is proportional to the velocity of the ground. Because of course the relationship between these two also has to do with omega. And it goes like this: SV is omega times SD. So that implies that if I know the velocity of the ground, I should be able to draw a spectrum. If you don't know the velocity of the ground, that's okay. You can work with the acceleration spectrum divided by omega squared and you obtain the displacement spectrum. Okay. Roughly speaking, this proportionality constant is about 1/2 for 2% damping. And for 5% damping is a little smaller, it's about 3/8, more or less, okay? So if I want a quick and conservative displacement spectrum, and I know the velocity of the ground is divided by 2, and that gives you the 2% displacement spectrum. Easy. All right, so with that in mind, I already have PGV. So I'm going to do the following. Let me walk you through this, because this takes a little bit of effort, or a little bit of explanation rather, not much effort. What I'm going to say is that I'm going to take PGV, which I obtained already for these earthquakes, divided by 2, that gives me the slope of the spectrum, displacement spectrum. Slope times period, which we calculated, and I asked you to remember. Slope times period gives me spectral displacement. Now, when this was first proposed, they noticed that when they were comparing calculated periods with measured periods, there often was a difference, number one. Number two, when this was first proposed, it was proposed to try to obtain conservative values, okay? They didn't want means or medians, they wanted sort of upper bounds to drift, because, hey, drift is scary, drift produces damage. And then there is a question as to what is the effective stiffness of a reinforced concrete element, because concrete cracks, right? Should we consider that somehow? I'll go back to that question in a moment. But for now, let me just say that to, again, obtain easy, safe numbers that sort of matched measurements, what was proposed by Shimazaki himself was to multiply the period by √2. Just gave him numbers that they thought matched the data well enough, and again produced relatively conservative numbers. And so for that reason, you can take that out of there and put it there like that. So you can think of this as sort of a safe estimate of spectral displacement, and spectral displacement times participation factor will give you, for a nice pastry and coffee, spectral displacement times modal participation factor gives you, come on guys, pastries are pretty good. I tell you, I've had like 3 by now. I'm getting fat from my Starbucks. Spectral displacement times modal participation factor gives you, say it loud, say it proud. No? I'm going to have to eat all the pastries. Professor Wang. You want pastry? Displacement where? Floor. At the roof, right? Yeah. Pastry for you. Let's see which one is which. Let's see which one is which. I don't give you a
Make sure you have breakfast tomorrow.
Oh yeah, no, I know. Yeah. Spectral displacement times modal participation factor gives you roof displacement if you have normalized the mode-shade factor to be 1 at the roof, which we've done. So that's a displacement of the roof. Hey, it says it right there. Okay. If you take that value and you divide it by the height of the building, this is the height of the building. My building has 7 stories, each one worth 365 meters. Then I get the mean drift or the roof drift ratio. The story drift ratio is going to be higher again, and we looked at that and we figured it's going to be probably 30% if not higher. So now we're approaching 2% in a single story. That's rather high. That would cause a lot of damage to partitions and so on. That begs the question whether you need to design a building to maintain functionality during an earthquake as strong as Kobe and so on. But I don't want us to get lost in talks about losses and probabilities and so on. What I really want us to agree on is that this is a very simple, in many ways, way to estimate drift. And it's very effective, again, because what you get from that is not very far from what you would get from detailed nonlinear dynamic analysis. That's how I started today. Believe it or not, what you get from that is not too far from what you will get from detailed nonlinear analysis. Questions? Let's talk about why there is a square root here. Again, when if you read Shimazaki will tell you the square root there is there mostly to make things work, to fit the data and give you an okay value. That's what Shimazaki says in his report. Very often, friends of mine, people who were close to Minnesota and who developed all this on the basis of the works of Shimazaki, Bonacci, Lepage, and others. Many people who were close to Sozen would say, oh no, but Sosen was also thinking about the effects of cracking on stiffness. Well, Sosen wrote something up that I'm going to try to summarize here for you. The question is, what's the right value of stiffness? Should we use the stiffness based on gross, uncracked sections, or should we use the stiffness calculated for cracked sections? Most building codes, most procedures out there use the stiffness related to the cracked section. Sosen asked this question once, which was very interesting. He says, look at these hysteretic loops. And you see them for a specimen that was cycled 4 times. And he says, this is the element when it's pristine. Of course, this is deformation versus force, or force versus deformation. When the element is pristine, it's very stiff. Of course, it cracks, and then it yields. So the stiffness related to the yield point, the stiffness that we calculate on the basis of cracked sections, the stiffness at that moment is given by this secant. Okay? What Sosen said in this writing that I'm quoting here and discussed many times with some of us is that, well, that happens once. And then after that, as cycles keep happening, the stiffness keeps changing. Eventually, you end up with an effective stiffness, if you will, when the building is moving back and forth. The effective stiffness, which he said is related to this peak-to-peak slope here, the effective stiffness is going to be very different from the stiffness associated with the first yield. The question is, why is this more or less relevant than other measures of stiffness? One of them being the stiffness before cracking. You could argue that stiffness is more relevant, but we've tried using that stiffness as opposed to as opposed to just using this. We've tried not using the square root, but calculating period on the basis of the cracked stiffness to see if we get better correlation between measured and calculated values. And so far, no luck. You don't get any better correlation. The period we calculated here is based on gross sections. Is it accurate? Well, no. Is it more relevant than, say, the uncracked, or rather, period calculated for cracked sections? Probably not. Maybe it's less relevant. But if it doesn't introduce any error, why not use it? If anything else, if nothing else, it is easier, right, to calculate. So I invite you to try numbers. If you don't like the square root here, if you think that's too much of a fudge factor, if you're convinced that cracked sections are more meaningful, or the stiffness calculated on the basis of cracked sections, fine, use that. Just replace this with the period calculated for cracked sections. You're going to get slightly bigger drift, though. But it's okay. We need to be conservative. They're not going to be twice as much. They're going to be 20% more or so, maybe 10% more, depending on the sections and so on. But I'm teaching you, or I'm trying to communicate the method as proposed by Sosen. And again, this correlates fairly well with data and not any better than you get otherwise. Okay? So, that's how we're going to calculate drift. Questions about that? Very easy, I think, very easy. Yes, you can do better. Yes, you can do nonlinear dynamic analysis and whatnot. But I assure you, it's always good to have, in the back of the envelope, this calculation to see if your analysis is any reasonable or not, right? Very good. Look, you know what I did? When I worked in a company in San Francisco for 3 years, from 2002 to 2005, I would always do this. And then I'd say, oh yeah, I think our analyses are okay. They look okay. The same thing with period and mode shape. Do not trust what's coming out of the computer before you try to run some numbers. Okay. Yeah.
Can you share some background about how that denominator 2 came from? The PGV divided by 2. How do you get that slope?
Yes.
Is that you got a lot of records and
Well, so Newmark in the 1950s, he was sort of the smart boy around the U.S. And because of that, the nuclear industry came to Urbana. Urbana's in the middle of nowhere. You may have been there. But they came to Newmark because he was a smart guy around. So Newmark collected about a dozen or so records, maybe a few more. And he plotted spectra. And then he looked at the shapes of the spectra, right? And then he noticed these ranges of nearly constant acceleration and velocity and so on. And what he did was to try to see what the so-called constant spectral velocity was. He divided that by PGV and he obtained amplification factors, right? And he produced the statistics on the basis of the 1 or 2 dozen records that he had. And the amplification factor for 2% damping and for sort of low probability of exceedance happens to be close to 3, which means the spectral velocity is 3 times PGV. Okay? All right. So let's do some simple math here, because this is actually kind of entertaining and it shows sort of the genius not only of Newmark but also of Sousa. So Newmark, if you read his reports that he wrote for the nuclear industry, he would say in the range of nearly constant velocity, you can get a fairly good value with low probability of exceedance by just multiplying PGV times 3. Okay? All right. But we don't care about velocity so much. We care about displacement more. How do we obtain displacement? We divide by omega, right? So I'm going to call this that, and I'm going to divide by omega. Omega is 2 pi over t. So I'm going to put the t here. Right? Well, Sozen comes to this point, he looks at this and he says 3 divided by pi, that's 1. That's how we got there. But if you go to the original reports by Newmark, you'll find a whole list of amplification factors, and you find, again, for 2% damping and a fairly low probability of exceedance, you get 3. Thank you. I think I have still one extra. Tell me. Great student, very, very good. Okay. All right. How about we talk about forces? Right? Because I've been ignoring that. Go ahead.
Just one comment to echo this, like the strength doesn't really matter that much. Because when we then learn structural dynamics, we have those prediction rule for displacement. Like when the structure period is short, like where you can use what we call equal energy rule.
Right.
But when the for mid period or long period structure,
Equal
where
displacement rule.
we have equal displacement rule. So no matter like what is the strength, but actually you get the same nonlinear displacement, the same as the linear displacement, which is kind of the thing we're talking about here, right?
It's the same idea with one difference, though. And the difference is that instead of using the equal energy thing here, we're just using a straight line.
Okay.
It's easy, and it works fine. Because the equal energy rule gives you values that tend to be a little lower here than the straight line. But yeah, just use the straight line. Easy. Okay. Well, you started going in that direction. You mentioned forces. Let's talk about force and strength. Again, it doesn't matter, but you have to have some. Kind of like money for happiness, right? Money doesn't buy happiness, but you have to have some. Never the same, I think, kind of thing. So let's go back to this frame. Maybe you don't care to trash all the partitions and so on. Maybe you don't care too much about drift, right? But again, everything has a limit. And if a frame like this doesn't have enough strength, you might get into trouble. So, or if nothing else, you still need to change, meet the codes, and all the codes require a certain level of strength. So what I want to discuss next is how do we think of strength in this context, right? And what I'm going to offer is the simple idea that the base shear coefficient should be above the threshold that at least the code requires right now. SA divided by some reduction factor. We should be able to exceed that. If nothing else, not to get in trouble with the law. How do I know how strong a building like this is though? Well, one way to go about it is to do the so-called pushover analysis, right? Despite its funny name. You can do that with Stera easily. You can say, oh, give me a triangular distribution of forces and push this thing sideways in a static fashion here. So you can just do that. And just like that, the Stera will tell you, oh yeah, the base shear coefficient, if you look at floor 1 here, or story 1, the base shear coefficient, that is shear divided by the weight, is about 0.1. Maybe a little bit more than 0.1. Say 11 or 12%, right? The idea is you would compare that versus SA divided by whatever number you're allowed to use as a reduction factor, right? And decide on that basis that whether you have enough strength or not. There are other people who have offered even lower limits than that, but I don't want you to get in trouble with the peer reviewers. At least you should be able to demonstrate that you can exceed the code. And if you design for drift, if you try to keep the drift low, say smaller than 1.5 or 1% for the 500-year earthquake, I assure you, just by default, even using minimum reinforcement, you're going to have plenty of strength. If you don't believe me, look at the appendix of this book, where we go through that exercise. Do you get enough strength when you just design for drift? And the answer is yes. But if you want to double check, and you want to make sure that you have a base shear coefficient that is big enough, then you can just push the button and make this run, and you get an estimate of base shear strength. Okay? Well, but how do you know that's right? Actually, it's not too hard. We can check that value by hand, again, like we've been checking other things. And if you go to the files I have given you, you'll find a file called, with a very creative name, estimating base shear strength. And I estimated the base shear strength for that one building there. I'm going to show you how I did that. So, I defined the yield strength of the reinforcement. This is the default yield strength in Stera, so I didn't change that. If you read through Stera, they tell you they amplify that strength a little bit. But anyways, so that's what Stera is assuming is the yield point for these bars. The beams in that particular example, I think I've shown you, the beams are 600 mil deep, and the cover measured to the bar center is 40, so I'm going to say the effective depth for the beams is that much, and that's about all I need to know to calculate the bending strength, so to speak, of this beam. I'm going to say I have two D22s. If you remember, that's how we started earlier. We looked at the beam reinforcement. Two D22s at the bottom, two more at the, sorry, two at the bottom, two at the top. I'll be careful with the top because there's some reinforcement in the slab to take that into account in a second. But at the bottom I have two bars. So for positive moment, I just have two D22s times Fy, that gives me the force in the bars in tension. And I'm just going to assume the lever arm is 0.90 easily. Is that how you calculate beam flexural strength here, or you go through the whole thing of D minus A over 2 and so on? Right. I invite you to go through all that trouble and you're going to get something very similar. I admire the Japanese in many ways, and one of the ways in which I admire them is that they don't bother with D minus A over 2 and all that. That's good enough. So that's the strength of the beam for positive moment. The strength of the beam for a negative moment, well, that one is a little bit trickier because I have the bars in the slab helping in tension. So I added 4 of those bars up there, and I do the same math. Force times lever arm, and I'm just, I don't like doing D minus A over 2. There are too many other things that are more important to worry about, so I'm going to say this. The beam strength for negative moments. Okay. So I know the strength of my beams. I'm going to assume that I have enough stirrups so nothing fails in shear and I can yield things before shear failures occur. I'm going to assume that I have good bond everywhere, good long development lengths, good hooks so nothing pulls out and so on. I'm going to assume that this thing, when it reaches its capacity, it does so by forming a ductile flexible mechanism. Okay. Now I need to figure out the strength of the columns. And again, I'm not going to draw an interaction diagram. It just takes too long. I'm going to assume I'm operating under the balance point. And under the balance point, all I need to do is, if I know the axial load, and all I did was to sort of distribute all the axial loads uniformly. I know that's not right. I know the exterior columns will see less axial load than the interior columns, but things are going to balance out. This is sort of the average axial load. And I'll explain why I say things are going to balance out. But that's the column cross section. If you remember, this is again how we started. We have 8 D22s, 4 in the corners, and 2 more on this side and 2 more on that side. That's a total of 8 bars. So what I'm going to say is that the moment capacity of the first story column is just this much. The area of 1 bar times Fy, so this is just the force that 1 bar can resist when it yields. I have 3 bars on one side of the column, so on this side I have 3 of those bars. On this side I have 3 of those bars, assuming I have tension here and compression there. I have 1 bar here, 1 bar there, and again, in this rectangle that they call X side, I'm saying I have only 2 bars, 1 on each side, so I end up with 1, 2, 3 bars. In the middle I have only 2 bars, so that's why I place a 2 there. These are the distances from those bars to the compression reinforcement. So I'm thinking of those as lever arms. And then the axial load has that much lever arm, just as much as the bars in the middle. And that gives me a very quick, very easy estimate of the moment capacity of the column. Again, if you don't like that, just draw the interaction diagram and enter with the axial force and find the moment. You'll find that's not too far off, usually. At least it gives me a sense or an order of magnitude, nothing else. That's not going to be 2,000, no way. For the top story, I do the same, but I realize that the columns in the top story are carrying less axial load, and that gives me less moment capacity, therefore. And I'm going to explain in a second why I'm looking at the first and the top story. This is the moment when I do this. What I'm going to do is the following. I'm going to assume that in the limit when I push this thing far enough with some distribution of force, when I push this thing far enough, eventually things are going to yield. And I'm going to assume, and we can debate this assumption and we can try different assumptions, but I'm going to assume that the beams are going to yield at their ends. And you were asking me about plastic hinges. There you go. I'm going to assume the beams yield at their ends. I'm going to assume the columns end at the bases, because what else can they do? Again, I'm going to assume the same for all the beams. Like that. All of them. All right. I'm going to have to think a little bit more about what happens at the top, though, because, say, at this corner, I have one column versus one beam. Sure, maybe, or most likely than not, the column, it's stronger than the beam, so the beam will probably lose that fight. But over here, things are different because I have two beams in one column. Unless I make that column quite weak, rather quite strong, it'll probably yield before the beams yield. So I'm going to assume I have hinges there and hinges here. And again, this is a fairly arbitrary mechanism. Come on, draw. Why don't you want to draw? Draw. No? All right, well, imagine there's a hinge out there. So I'm going to assume that if I push this thing sideways far enough, it will yield like that. And if it yields like that, it ceases to be a structure of the kind we work with all the time. It becomes a mechanism. Right? Like the ones that mechanical engineers work with all the time. Doesn't want to draw. Oh, I see. The program crashed. That's why. Oh, not only the program crashed, the computer crashed. Oops. Yeah. Well, I'm going to have to restart my computer. Oh, that sounds good. Just towards the end. What can I do? Nothing. So nothing's working. Well, Control-Alt-Delete. See what happens. Nothing. Not even that. And it crashed. Well. Push the button. Push the on and off button. Yeah, no, nothing. All right. I have to push the button. Let's hope it comes back on. Well, it comes back on. Let me try to narrate what I want to do. Yes, there's some signs of life. I see a little light. So what I want to do next is, now that I have a mechanism, I'm going to impose a virtual deformed shape on it. Virtual, meaning it's not related to the actual deformed shape of the building. In a way, we're talking about very small, infinitesimal, fictional, imagined deformations that I'm going to use to, oh, I see, that's why. Windows did this to me, Mr. Gates. Thank you. After this. I'm going to impose a virtual shape on this thing, and I'm going to use a concept that I'm sure all of you are very familiar with, which is the concept of virtual work. So the idea is going to be that the work done by the external forces through the virtual displacements I'm going to impose on the structure should be equal to the work occurring internally in the structure. Because I have a mechanism, all the deformations are going to occur only in the hinges that I'm assuming are going to happen here. When I equate internal and external work, that's going to help me find base shear strength. If I assume I know the distribution of forces acting on this thing. That's what we're going to do, if my computer cooperates. Wow. So I'm saying again, getting Windows ready. There we go.
0%.
Yeah. Are you guys familiar with this type of analysis? Some people call it mechanism analysis. Some people call it plastic analysis. We call it limit analysis. Are you familiar with this type of analysis?
Yeah. Very simple structure. Maybe.
Yeah.
So Santiago, we have some time. So let me ask that you show us that the dual system with a fracture wall and a frame. But in Japan and Taiwan, we might have a complete frame, and the reinforced concrete wall is infilled within the panel. So in this way, I believe the shear wall will become much stronger compared with fracture wall.
Yeah.
Yeah. So do you have any experience? Maybe in your simple analysis can handle this kind of problem?
Yeah. But you can, for period, you can operate the same way we've done here, counting beams and columns. For strength, in the book we have that exact example.
Oh, I see. Okay, good.
Yeah, the beams interacting with the wall make it stronger. Wow. But that has a sort of a negative effect in that you don't want the wall to be too strong, because then the shear goes up, right?
Yeah.
But I wanted, that's one of the things I want to discuss here. I want to show you an example in which we have a wall connected to beams. I try to take into account that extra strength that you get from that. And even with that, and even with higher mode effects and so on, you can still design it for shear.
I see.
Yeah, that's where I'm going.
Okay.
It's a good thing I didn't type the password for my for my username. Do you ever do that? I do that all the time. God. Come on. All right, I need to think of another story to tell you. Oh, well, let me, instead of telling you a story, let me ask you a question. So you saw the data we're getting from Chile, and this is not just from a couple of hospitals. They have dozens of hospitals that they inspected after earthquakes. And you saw they're reporting more damage in the ceilings and light fixtures and so on in the frames versus the wall. What's your reaction to that? Because that's opposite to what all the literature says, right?
Very surprised.
Right? Yeah, very surprised. At the same time, when we look at the ceilings we're testing at the University of Canterbury, what we see is that the ceilings interact a lot with the walls, where the ceiling meets the wall. At least in New Zealand, they connect them, the ceiling and the wall. They don't move independent from one another. At least they connect a couple of edges. And that interaction causes a lot of damage. That interaction is drift related, drift driven, as opposed to acceleration related. So, yeah.
So what you're saying is because the drift, when the drift is large, it's easier to damage, even its ceiling.
That's what the evidence seems to be suggesting. I guess we'll see when we run the tests in Tainan starting next week. We have ceilings, we have sprinklers, we have shelves and all the things that are supposed to be acceleration sensitive. And again, we can reconfigure the test specimen by introducing or removing the braces. That should create more or less drift and more or less acceleration. So we'll see if there's consistency between that and the field data from Chile. I'm a little, my reservation with Chile is that in Chile they use sometimes infill wall that is made from masonry, and that sometimes acts very much like a concrete wall, so that may be increasing the accelerations even in the frames. When I mentioned this to my colleagues, they said, no, even when we remove the cases where the infill is made out of brick, and we only look at infill made with drywall or gypsum board, you still see the same problem. So, yeah. All right, let's see if we can finish here quickly. This shouldn't take too long. So, yeah. So we have a mechanism, or no, we're going to assume a mechanism. But now everything's going to pop on the screen. Yeah, that doesn't help. I need this other thing. I need to go back to my picture. Yeah, all right. So there's our mechanism. Not now. Yeah. And I need to now impose a virtual shape on this. See if I can. This is the virtual deformed shape I'm going to introduce on this. Like that. We're going to assume everything rotates about the bottoms of the walls like that, such that the beams will be rotating like that. And I'm going to assume that this virtual shape is such that this is 1 here. Because the deformations are going to concentrate on the hinges only, I'm going to assume the column remains straight. And I'm going to assume this is a straight line here, that the distribution of forces is triangular. But we can change that. Okay, so with that in mind, thought I had opened that already, but no. I see, it doesn't matter. Everything is going against me. Why? Come on, you can do it. Maybe I should just open it like this. Ah. Give up. Maybe we need to start from here tomorrow. I don't know. What's going on with my computer? Why doesn't it want to run MATLAB?
How about we do some QA instead? And
Okay,
we
let's
start
do some
from here
QA.
tomorrow.
I'll try to pick up from here tomorrow. Go ahead.
Yeah. So, do we have any questions you want to discuss with Santiago? Looks like everyone wants to have their dinner.
Yeah. Yeah, I'm sorry, I don't know what's wrong with my computer. I'll try to fix it tonight. Yeah, thank you very much.
Okay. So let's put our hands together. Thanks, Professor Pujol. So we'll see you tomorrow.